Okay, so this is net forces example number 1. So I have 3 forces acting on an object. One force is 30 newtons at 75 degrees. A second force is 16 newtons at 205 degrees. And the third force is 25 newtons at negative 85 degrees. What is the net force acting on the object? Okay, so let's first represent what these forces look like on an object in a form that we call a free body diagram, and there's some mini lectures and examples of a free body diagram and how to develop one of those. We don't need to do that to just calculate the net force, but I think pictorially it'll help us visualize that net force calculation a little bit better. So net forces are just vector algebra. So we've really hammered this in chapter 3, and now we're going to use it in a practical application, sort of looking at how a net force is on an object. And once we do that, then we can see what the acceleration and the motion of that object is as a result of that net force. Okay, so let's get started. For force number 1, I'm at 30 newtons at 75 degrees. So let's first draw a coordinate system to help us maintain and keep reference of those angles. So 30 newtons at 75 degrees. So let's say that's here. Here's my 30 newtons. Here's my angle of 75 degrees. Force number 2 is 16 newtons at 205 degrees. So that's in quadrant 3. 16 newtons at 205 degrees. So we'll represent that like that. Slightly half the size of the arrow. It's about half the size of the force. And force number 3 is 24 newtons at negative 85 degrees. So that's in the 4th quadrant. A little bit longer than my 16, but not quite as long as my 30 newtons. And this is negative 85 degrees. So there are my 3 forces acting on the object. Now, like in the introduction to net forces, I'm going to number these forces. We will start with number 1, 2, and force number 3. And in order to add these forces together, remember net is the sum of the forces. In order to add them together, I have to add them as vectors, which means I have to pull apart their components, add the components together, and then put them back together. So we will look at both the horizontal and the vertical components for each of these forces so that I can add the horizontal components together, add the vertical components together, just like we've practiced adding vectors. So force number 1, it's at 75 degrees with respect to the horizontal positive axis. So it's 30 times the cosine of 75 degrees will give me my horizontal component, and 30 times the sine of 75 degrees will give me my vertical component. So 30 cosine of 75 is 7.76 newtons, and 30 times the sine of 75 is 29.0 newtons. So it's 28.97. So if I round to a single decimal point, got 29.0 newtons. They're both positive, as they should be. I'm in quadrant number 1. All right, force number 2. Force number 2 is 16. The angle is with respect to the positive x-axis, so I can use my sine and cosine as horizontal and vertical respectively. So I have 16 times the cosine of 205 newtons horizontally and 16 times the sine of 205 newtons vertically. So 16 cosine of 205 is equal to negative 14.5 newtons, and 16 times the sine of 205 is equal to negative 6.8 newtons. Now both components are negative. Does that make sense? Well, my force is in the 3rd quadrant where both the horizontal and vertical components are negative, should be negative. And so it's consistent with what I expect. Force number 3. Force number 3 is also given with respect to the positive x-axis, so I can use my sines and cosines for vertical and horizontal respectively. So I have 24 times the cosine of negative 85. And it's important to keep that negative in there. It'll help me get that sign. That should make sense. And 24 times the sine of negative 85 should give me my vertical component. So 24 times the cosine of negative 85 gives me 2.1 newtons. And 24 times the sine of negative 85 gives me negative 23.9 newtons. So I have a negative vertical component, a positive horizontal component. That tells me I'm in quadrant 4, which indeed I am. All right, so now that I have my horizontals and verticals separated, I can just add them numerically. So we have 7.76 minus 14.5 plus 2.1. I get a net horizontal component of 7.76 minus 14.5 plus 2.1 of negative 4.64 newtons. Vertically, I have, I'm just going to put a little barrier there, 29 minus 6.8 minus 23.9. And for my vertical components, I get negative 1.7 newtons. So that tells me that my net force has a horizontal component. The net force, horizontal, is equal to negative 4.64 newtons. And my net force, vertical, is equal to negative 1.7 newtons. So those are the components of that force. How do I get the magnitude of the force? Well, I have to use Pythagorean's theorem. So the magnitude of my net force is equal to the square root of the horizontal component squared times the vertical component, or plus the vertical component squared. So I have negative 4.64 squared plus negative 1.7 squared. And the magnitude of my force is equal to 4.9 newtons. And that's been a while since I've actually done that one. I just have the answer key over there, so let's just double check it. Negative 4.64 squared plus negative 1.7 squared, 4.9. All right, 4.9 newtons. If that's not enough, I also need the direction. So to get the direction, I take the inverse tangent of the y component, negative 1.7, over the x component, negative 4.64. And when I plug that into my calculator, I get an angle of 20 degrees. Now, I have to pause and say, does that angle make sense? That means I'm in quadrant 1. But both my vertical and horizontal components are negative. I'm in quadrant 3. So how do I get to quadrant 3? I add 180 degrees. So I have a total of 200 degrees for my angle. So the net force is obtained by taking these vectors, breaking them apart, horizontal and vertical, adding those horizontal and vertical components together to find the component horizontal of the net force, the component of the vertical net force, putting those back together in the magnitude using Pythagorean's theorem, and putting them back together in the angle, but recognizing we have to check that value out of the calculator with our component directions so we know that we're in the appropriate quadrant. If we're not, we add 180 degrees to get to that quadrant. All right, good job.